Okay. Today, we're starting our new quadratic functions. This may be the last unit that we do. As I stated in the blog, if you read the blog before, this unit plays off of the last unit we did. It uses lots of the same concepts and skills, which is why we do the linear functions first. Linear functions are a simpler function than quadratic. A linear function is a straight line, and a quadratic function is a little more complex. It's actually, the picture of it is a parabolic shape. It's a U shape, like a cup shape or an overturned cup. And it's a more sophisticated function, and it has different applications. We'll see when we flip open the first page. So why do we study quadratics? Well, quadratic functions are used to model many situations in our everyday life. You just take a look at the pictures that you see here. This is a picture of the arc that water makes when it comes out of a water fountain. This bridge, you can see the span of the bridge, the supports are in these, well, this is a half of a U shape. This is a parabolic shape here, okay? And then this, if you can see, is a contact lens. A contact lens itself is a disc shape. It's a parabolic shape. So all three of these applications would use qualities of a quadratic function in order to model and to work with them. If you also see this, a TV cable dish, it's actually a parabolic dish, a receiver that you get your cable on. It's also in the shape of a parabola. So in order to construct these discs or construct a contact lens or build a bridge, you have to have an understanding of quadratic functions, and quadratic functions are used in the composition of these shapes. So the words that we're going to be encountering in a quadratic function unit, it's much more complex than a line. Like a line is just a straight line, and lines are either trending upward or downward or just straight across. Parabolas will be opening upward or downward as well, but they have different words associated. We're going to have the word vertex, the leading coefficient, end behavior we've seen before, y-intercept we've seen before. We've seen the word x-intercept before for linear, but parabolas, quadratic functions, sometimes have two x-intercepts. We've also talked about the word range as well. So the shape that a linear function forms is a line. The shape that a quadratic function forms is a parabola, okay? It's a distinct shape. It's a cup shape or an inverted cup shape. So we're going to use our graphing calculator to determine which of the following are quadratic functions. So these are the skills you're expected to know now, quite handily. So pick up your graphing calculator or your graphing calculator simulator and clear it out, clean it out. And the first thing we're going to do is enter in this first equation. And the first thing I have to do also is tell you where the y squared is as well, right? Or the exponent button. So we go to our y equals menu, right? These are all y equals statements. And let's enter in 0.02. It says x squared. Well, there is an x squared button on your calculator right here, so you can just press that one. Whoops. I screwed that up, didn't I? 0.02x, and then you can just press the x squared button if you want. Subtract 3. So let's take a look at the graph. I'm not going to change the windows at all. These numbers look pretty small. So if I press the graph, I do see this parabolic shape, right? Let's change the windows a little bit. Let's change the windows, the x windows, x min and x max. Let's change x min to -20 and x max to +20. And let's see what we get here. There we see that parabolic shape, right? It's like a big cup. So it asked us to determine which of the following are quadratics. As long as you get the cup shape or the overturned cup shape, it's quadratic. So I'm going to check off that, yes, that's a quadratic. I'm just going to do a check mark. Now let's check the second one. I'm going to just clean this out. This one is 2x. It's cubed though, right? It's not squared. So I can't use the squared button. I have to use my exponent button. And it's an exponent 3. Now when you enter your exponent button in, the cursor is going to stay up there because it doesn't know how big you, whoops, sorry about that. I'm going to redo this one. I'm going to clear out. Sorry, I'm going to clear everything out. Sorry. Okay, let's start over again so you can see everything I'm doing. I'm going to go into the y equals screen. I'm going to enter in 2 word linear. This is a linear function. This was quadratic. This was also quadratic. This is a cubic, that kind of funny snake-like thing. All right, let's check this one. Go to your y equals, clear it out. And I'm going to get negative 2x bracket x squared plus 1 close bracket, graph. And again, that funny snaky thing, that's not quadratic. It's another cubic. And the last one, clear, x bracket x subtract 5 close bracket. Take a look. And again, it's another cup shape, right? So this also is quadratic. So this was a cubic, that funny snake shape. We'll study more of those in grade 12. So what we have here, we have 3 quadratic functions. So let's take a look at them. We just finished talking about linear functions. So this is the form of a linear function, right? Ax plus b. Now we see quadratic functions. What can we summarize about quadratic functions? They either have an x squared in them, right? Or they have 2 x's. And that kind of makes sense because if you think back to our polynomial unit that we did at the beginning of this course, an x times an x does give me an x squared. And here I would have x multiplied by x giving me x squared. So a quadratic function appears to have an x squared term in it. And that's exactly what defines a quadratic function. So next thing, it's going to ask us just to get a little more practice on quadratic functions. And we're going to sketch a quadratic function using intercepts. Sketch the graph of this quadratic function, label the y-intercept and the x-intercept. So that's interesting as well, right? And sure enough, just as we summarized on the previous page, quadratic functions don't just have an x in them, an x term. Quadratic functions have an x squared and then sometimes an x term. So if I just had these 2 terms given to me, this would be a linear function. With that added x squared term, it becomes quadratic. It becomes that cup shape. So let's clear our calculator out, like second plus sign, number 7, number 1, and then number 2, and clear everything out. And we're going to enter this equation in. X squared, I can use the x squared button, plus 2.25x subtract 7.88. Okay, and let's see what our graph is. All right, it's got the cup shape, right? The cup. And we would say like pointing upward, right? So this graph is pointing upward. It wants me to label the y and the x-intercept. So that's what I have to label on my axes. I have to label the y-intercept and then the 2 x-intercepts. If you recall from linear, it's always easier to go for the y-intercept first because that's just a matter of second trace value and you put your 0 in, right? So I get the y-intercept is negative 7.88. And just like the linear function, if the quadratic is given to me in the proper form, like the x squared, the x, and the constant term appears to be the y-intercept. Okay? So to find the y-intercept, remember what we did? We did second, trace, value, x equals 0, and we got a y-intercept of negative 7.88. So I don't have to worry too much about a scale for my y-intercept because that's the only y value I'm going to record. So I'm just going to call this negative 7.88. And that's where the graph crosses the y-axis. It's a little trickier to do the x-intercepts because I have two of them. I have this x-intercept and this one. I guess because we're just learning right now, I'm going to just draw my picture sort of as I see it, right? I'm going to do one x-intercept closer than the other one. So let's see what these two x-intercepts are first, right? So I guess just in order to do my quick sketch, I'm going to have, notice the turning point is underneath. So it's going to be, I'm going to just sort of draw it as I see it. A very quick sketch. I'm just reproducing what I see. Notice that this x-intercept is closer to the origin than this one, so this will be a smaller number than this would be. This is a small positive number, this is a larger negative number. All right, and we're gonna actually, so here's my y-intercept that I've labeled. Now I have to label this and this. Notice this is a parabola, a quadratic pointing upward, and this graph extends forever and ever. So it's very important that just like the lines had arrowheads on the ends of the lines indicating that it grew forever and ever, you have to put arrowheads on the ends of the quadratic as well. Now let's find the x-intercepts. Do you remember how to do that? Well, we only found one x-intercept before, but a parabola often has two, and it was a different procedure. I enter y2 equals 0 first, and then I go to my second trace menu. And then I use option 5, intersect. And I basically enter. I answer those three questions, right? Okay, so let's try that. In my y equals statement, I leave my first statement in, that's my quadratic. And I want my y2 statement equal to 0. And then I'm going to press second trace, number 5. And I'm going to find out, this is where the cursor is right now. It's usually left on the y-intercept. That's the last thing we did. So I'm going to use my back and forth arrows and send it up to where my first x-intercept is. Now I'm going to answer the three questions that I respond, enter to, right? Is this my first curve? Is this my first statement, the y1 statement? Enter for yes. That was the second y equals statement I entered in, right? y2 equals 0, yes. And now they want to know if I want to take a guess at that point, and I do. And it tells me when y is 0, so that's telling me I've got the x-intercept. Well, x is negative 4.15, I suppose. X equals negative 4.15. I'm rounding to 2 decimals. So that's what I'm going to label right here. This x-intercept is negative 4.15. Okay. Now I have to find this second x-intercept. So let's try that one. I go through the same process, right? It's nothing different. Second trace number 5. But this time, I've already found this intercept. I have to use my back and forth arrows to move over to my second x-intercept. And here we go. Now I answer the three questions. Yes, yes, yes. So this x-intercept is 1 point, wow, if I round it to 2 decimals, I guess it would be 1.90. Okay, so this is my second x-intercept. And that's the trickier thing about quadratics. Quite often there are two x-intercepts. We're going to see that not every parabola has two x-intercepts, but a lot of them do. That makes it a little more time-consuming to work with quadratics than the linear functions were. So there we go. We sketched the graph of our first quadratic. We found the y-intercept the very same way. We found the x-intercept the very same way. The difference was there are two of them now. Okay. So let's try one more. Let's try example 3. Okay, first thing we do between questions is we clean our calculator out. So it's nice and clean. Okay, I'm going to take a look at this one now. So here's my cleaned out calculator. I press y equals. Ooh, I thought I cleaned it out. Sorry, guys. Okay, now when I press y equals, it's nice and clean. So I'm going to enter in negative 2.65 x squared plus 3.9 x plus 12. And let's take a look at this one. Now, this one you can see is a downward facing parabola. Parabolas, which are the pictures of the quadratic functions, that's what we call the shape. The shape is called a parabola. They're either pointing up or down. So there'll be an up or a down. That's it. They're not sideways. They're either up or down. Very similar to the linear, except in the linear, do you remember in the linear functions we had an upwards pointing, a downwards pointing, and then a flat? There's no flat parabola. They're either going to be pointing up or pointing down. So I do think that we need to see the y-intercept. I can't see the y-intercept. So once again, I'm going to have to adjust my windows. The top of the window would be controlled by y max. So I'm going to change my y max. I'll put a 20 in, right? Other numbers might have worked. Let's see if 20 works. Perfect. So I'm just going to record this. I think this x-intercept is a little closer to 0 than this one. I see the peak, the turning point of the parabola is not quite on the intercept. So I'm going to do my sketch first, and then I'll add in the, when we do more formal graphs later on, that are actually modeling questions and things, you'll be expected to do proper scales. But this is, whoa, sorry about that. This is just a very quick sketch. So I have to label this point and this point and this point. All right, let's see what we got here. Let's go to our second trace value, put a 0 in for x, and we get 12 for y. Okay, that was nice. And that's our y-intercept, 12. It doesn't matter which x-intercept you go for first, so it really doesn't matter. But I do have to put my y2 equals 0. Without that y2 equals 0, I can't answer the 3 questions, right? You need 2 equations because you're trying to find the intersection of these 2 equations. Just to backtrack here, when I find my x-intercepts, I enter in the parabolic equation. Then I'm also entering into the calculator the y2 equals 0 equation, which is just the x-axis. Then when I go to my second trace intersect, I'm telling the calculator to find the coordinate points of the 2 intersection points, right? Okay, so now second trace, now I'm going to find where those 2 equations intersect each other. Now, as before, usually when you do that, your cursor is left on the y-intercept. Just move it down to the whatever intercept you want to, x-intercept you want to tackle first. Now you answer the 3 questions. So my first x-intercept is negative 1.52. Okay, negative 1.52. And I'm going to repeat the procedure for the second x-intercept. So second trace, number 5. Now, I've already got this cursor. I have to move everything over, or move the cursor over to the second one, and then enter, 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 and I get 2.99, okay? 2.99, and that's it. All right, so really all the steps, you can see why I said the steps were they're identical. The steps are identical, but you're dealing with a different shape. And because the different shape quite often has 2x-intercepts, we have to do that process twice. Now, the other thing I want you to notice is notice the leading coefficient. The leading coefficient is always the coefficient attached to the highest power of x. In linear, like without this x squared here, this equation would be linear. And when we were talking about linears, if the a value was positive, the line slanted upward. If the a value was negative, the line slanted downward. Similarly, for parabolas, I look at the lead coefficient, which now will be the coefficient of the x squared term. If the lead coefficient is positive, and this would be a positive 1, right? The coefficient on the x squared. The parabola opens upward. If the lead coefficient is negative, the parabola opens downwards. So I'm going to put a little note here. Notice the lead coefficient is negative 2.65. A negative lead coefficient means the parabola, which is the name of the shape of a quadratic function, opens downward. Right? It points down. And then here, there's no lead coefficient noticeable, so it means it's a positive 1. Notice the lead coefficient is positive 1. Positive 1. A positive lead coefficient means the parabola opens upward. Okay, so that's something to note, very similar to the rules of the linear functions. Let's talk about a few characteristics, and then I think I'm going to call it a day, because this is kind of a lot to take in, I think. So characteristics of quadratic functions. What should you be noticing when you study these things? What should you notice? What should jump out at you? Okay, we've got a new term here. The vertex of a parabola is the point where the direction of the graph turns, sometimes called the turning point. So we can see that this is the vertex right here, right? This point right here. It's where the parabola changes direction, right? If I were to draw this parabola, my pen would be making a downward motion. As soon as I hit the vertex, my pen would start to swoop upward. So that's called the turning point, right? The change in direction. Every parabola has a vertex. Okay, and it's a point, right? It's a coordinate point. So every parabola has a vertex. Every vertex has an XY coordinate point. The vertex is an important point of the graph because it's where the maximum or minimum value of the graph occurs. So what does max min mean? Well, the word minimum means lowest point, right? Lowest point, highest point. Maximum means highest. If you look at this parabola, the parabola, the function itself, my pen is making a direction. It stops at the vertex basically and then turns and moves upward. So the function itself never drops below the y value, because we're talking about vertical movement here, a y value of 0, right? For this parabola, the function never reaches a value higher than a y of 4, right? And this function never reaches higher than a value of 2 on the y-axis. So that's what we're talking about, maximum and minimum values. So that's going to change a few things that we, from what we learned with linear functions, right? Linear functions were unbounded. They grew forever and ever in the up-down direction and forever and ever in the sideways direction. So we know that x and y intercepts are important, but I think the vertex might even be more important than x and y intercepts. If we know the vertex and the direction of a parabola, we know a lot about the location of the function. So let's take a look at these pictures. We've got two parabolas that open up, two parabolas that open down. And we're going to talk about domain and range. Remember, domain were all the possible x values and y were all the possible y values. So for each of the following graphs, the vertex and the range are shown. So we've got the vertex. The vertex is what? X is -2, y is 0. Now the domain is XER. You'll notice that the domain of all of the quadratic functions are XER. Quadratic graphs grow forever and ever sideways. So the domain will always be XER. Maybe I'll add that in. Quadratic functions grow infinitely without any bounds from left to right. Okay, that's sideways. Arms, not only are these little arrows pointing upward, I suppose you could say, they're actually pointing sideways. So they never stop growing sideways. So we say the domain is, just like in lines, XER. X can be any real number. However, the range is limited, right? Because we have a max and a min, the graph doesn't grow forever and ever up and down. It grows forever. An upward-facing parabola grows forever and ever up, but it stops somewhere wherever the vertex is. That's what its minimum value is. Okay. Here, minimum value of -6, right? We say the minimum value is 0. That's the lowest value for y. Here, the minimum value is, well, the graph doesn't go below -6, so we say the minimum value is -6. Here's last example, and then I'm going to let you catch up on any other old homework. And remember, when you finish a previous unit, if you finish linear functions or the trig, let me know and I'll send you a test. Because you're sort of working at your own speed here, right? Let's analyze these two quadratic functions. State the vertex and the range. Well, let's see here's the vertex, right? The vertex has a coordinate point. The x value would be 5. And then the y value is 1. So that's what we would say the vertex is. The domain, well, the side-to-side growth is always going to be XER, so you don't have to think about that for quadratics. But the range are all the possible y values. Well, the lowest value that y can ever get is 1, but it grows forever and ever infinitely, so we say to infinity. The 1 is included, and the infinity symbol is not. So that's one way to write the range. The other way we could write it is, or we can write the range as, we can say y is going to be greater than or equal to 1, right? That's another way we can write the range, whatever way you prefer. Let's take a look at this one. The vertex is, well, it's 5 again, but it's 5, 4. Domain is always going to be XER. This time the range is the hat notation. You might be more familiar. So I would say, well, y is -4 is the lowest, and it just gets bigger. So y is greater than or equal to -4. Either one of those is fine. Okay. All right, I'm going to let you absorb and maybe just look at some of these words and concepts and play around a little bit with your simulator if you need to practice getting your x and y intercepts. Right now, that's what you need to be really, really efficient at, getting x and y intercepts. Remember, you can always email me with questions or pop into the Google Meet. We'll continue on tomorrow. Hopefully I can touch base with a couple of you and see how you guys are doing. Right? Okay, that will be it for the video for today.